Hello, welcome to the latest episode of Data Unchained. I'm your host, Molly Presley. As you can see, we're recording today from a convention center. We're in Atlanta, Georgia at Supercomputing 24, and really focusing the conversations today on GPU computing, putting large data sets to work in your AI and HPC models. But before we go into that, let me tell you a little bit about the show. So Data Unchained is really focused on, as data has become increasingly decentralized, that the mainframe and the building that used to be kind of the critical mass of everything data has now spread out where we have multiple data centers, hybrid clouds, even data being generated on sensors in space and sensors in the laboratory. We're focusing on how do you harness that data and put it to good use in your environment. Today's guest is a gentleman who knows an awful lot about this space. Gary Greider. Welcome to the show.
Thank you.
So Gary, tell us a little bit about your background as a technologist and in the HPC space in general.
Well, I spent the first part of my career as a storage administrator and a storage person that builds storage systems for a living and manages them. But this was really a long time ago in the 80s. And so, storage was mainframes then, right? But then more recently, I've in the last 3 decades of my career, I've been involved in DOE's planning for all of our storage for the whole of DOE really, and the HPC part of DOE. And there's sort of 2 pieces of DOE. There's the Office of Science part of DOE, and then there's the NNSA part of DOE. And I work for the NNSA part, which is the nuclear part of DOE. And there's a counterpart to me in the Office of Science part of DOE, and so I've been responsible for helping DOE manage technology development investments for 25, 30 years. So I've seen an awful lot of technology, and somehow I had my hand on a lot of technology over the years, courtesy of DOE funding it.
And I think before we talk a little bit about the company or the group you work for, you have worked on a lot of file systems since really the genesis of those file systems. I think it's kind of interesting to maybe talk about, you said earlier when we were getting ready to have a conversation, it's easier to talk about the ones you haven't been involved in than the ones you have, but maybe talk a little bit about what you've done in the file system world.
Okay. Well, in the 80s, I helped work on and commercialize in some way a thing called CFS, Common File System, which turned out to be called Data Tree, which was then offered up by General Atomics as a storage system solution. And then its distant cousin was Unitree. Most older people know what Unitree was, but these were all HSMs, if you will, that lived in the 80s. Then, we started working with IBM, and IBM was working on this thing called the IBM VM Workstation Data Save, big long name in it, and that turned out to be what they now call Tivoli or TSM. And I actually did a bunch of work in that space. We ported the client to Unicos, which was the Cray Unix file system operating system at the time. I did the original port of that code to Linux. Linux was this brand new thing, and everybody thought we needed it to be ported to Linux. I also wrote support for using SDK libraries with an IBM product because they didn't like one another at the time. And so anyway, that was the 80s. In the 90s, we replaced that whole common file system data tree thing with a thing called HPSS, High Performance Storage System, which most people know of as one of the only true parallel archive technologies. There's others, but it's probably the most famous. And I did an awful lot of work in that space too, managing people that built part of that solution, and we still run that solution today for parallel tape. So that was a decent part of my 80s or my 90s work was in that space. And then along came clusters, very big, huge clusters in the late 90s. And we needed parallel file systems. And so we, started a fairly large effort in the late 90s to try to get parallel file systems built. And of course, in DOE, we don't just build one, we build multiple so they can compete with one another, right? And so we put out this RFP, and the RFP was about, does anybody want to build a global parallel file system for us? And at this big conference in Santa Fe in 1998, and everybody that could spell parallel file system in the world came, which wasn't very many, right? Because they didn't know what it was.
Or two
and
handfuls,
we got accused of, asking for the intergalactic file system and all sorts of fun names. But people that showed up were people like Garth Gibson, who founded Panasys, after he heard about our thing and said, oh, geez, you guys are writing up all the specs for what a parallel file system ought to look like. Mm-hmm. I'm going to form a company and do that, right? And so Panasys came from that effort. Certainly, we helped take GPFS way further down the road than it was, originally had gone. And we also funded this thing called Lustre. You may know what Lustre is. Lustre's probably used on still the top, 50 supercomputers in the world. And it was invented primarily for checkpointing, so very, very large-scale checkpointing. And that was a fun project I worked on with a really good friend, Peter Braum, who invented it. I think I spent 5 years of my life every Thursday morning with Peter getting Lustre right. Mm-hmm. We also had a lot of university activity that we funded in that space and time. And one of the things was PNFS, or NFS, what is now NFS 4.2. We started that effort in 2002 with the University of Michigan, and that's actually where Trond worked. So
amazing.
That was a long time ago, 24 years or something. And we funded them for about a decade to do a lot of the underbelly that sits in PNFS today, so compound RPCs and other kinds of mechanisms that we had put in there. And then we also funded other university projects. So one of them you may have heard about, this thing called Ceph. There's booths that are selling Ceph now.
Yep.
Ceph is an object server kind of today, although there was a file system associated with it. There's an interesting story. It was University of California, Santa Cruz, and Sage Wild, who's the author of Ceph, was a graduate student at the time. And we funded them to look at scalable security in file systems and scalable metadata in file systems. And they didn't do either one of those, but they did build some really cool technology in object land, and so that became what Ceph is today. And we funded things like MPIIO. You probably know it's a parallel middleware thing. We had a whole lot to do with HDF5, which is a middleware for formatting in parallel and things like that. Later on in the 2000s, we got involved in all kinds of analytic kinds of things. So we started working with the Apache Analytics community to try to provide back-end storage systems that worked well in that space. We were doing that for DOE and DOD. And then most recently, things like Hammerspace, right? Because it's a follow-on essentially to the early PNFS work and has a lot of promise in providing open, protocol-oriented parallel file system, which kind of has never been done. Mm-hmm. There's never been an open protocol-based, variant of this. So we're hopeful.
So tell us a little bit about all that experience is now filtered into your work at Los Alamos. Maybe talk a little bit about who Los Alamos is. A lot of our audience will know, of course, but maybe some of them don't. Maybe share a little bit about who Los Alamos is and how they're tied, to kind of some of these broader initiatives that you fund. Los
Alamos National Laboratory is, if you watch the movie, you probably know what it is. But it's a nuclear weapons laboratory. There's a piece of DOE that's the nuclear weapons part of DOE. And there's 3 national laboratories that work in the nuclear space: Livermore, Los Alamos, and Sandia. And then all the other DOE labs, Oak Ridge, Oregon, all those things are Office of Science laboratories, so they're cousins, if you will. Why do we have big computers and why do we need big storage? Well, we stopped doing testing of nuclear devices in 1992, and there was a good reason for that. And So the question is, how do you continue to do testing on aging nuclear weapons and not do that with testing? So you have to virtually test. And so we virtually test nuclear weapons and give them, aging issues and see how they react and make them safe and make them secure and make sure they're going to work and all that kind of stuff. But we do that without, full-scale testing. So that takes a really large simulation to do. Los Alamos lives on kind of one end of the spectrum of simulation. If you take your average, your Office of Science National Laboratory, like NERSC, for example, they might have 3,000 users and 800 or 1,000 different simulation codes. Los Alamos has more like 4 simulation codes and hundreds of users. And at any one time, small numbers of them are involved in doing a simulation. And what does that mean? That means that the simulations are really, really large. So it's nothing for us to run a simulation that may occupy 10,000 nodes and a petabyte of DRAM for 6 months. So it's a
staggering amount of time.
So that's kind of unusual. So DOE has a wide variety of workloads, and we live on this one end of the spectrum. But what that does is, if you're dealing with 10,000 nodes for 6 months, that's a petabyte of DRAM, and you've got to find a way to deal with a petabyte of DRAM that's changing all the time. So Los Alamos has been required, because of our mission, to try to be really good at storage and I/O, because this is our world. This is what we deal with day in and day out. And so our mission has sort of made us focus in the data management area, perhaps more than most other laboratories, and it's purely driven by the workloads and the like. And so anyway, our job is to keep the weapon safe, and most of that work is done through simulation.
Big supercomputers.
And DOE supports this work, and of course, all the national labs have big supercomputers for their workloads, and there's a lot of commonality. I mean, everybody has big data. Ours happens to be big single petabyte size files, but other people have other kinds of problems. So they encourage us to work together, work with industry to develop solutions that will solve our problems. And DOE is really good about, and if it solves our problems, couldn't it solve other people's problems?
Right.
So we're encouraged highly to make our solutions reusable by the rest of industry, and to actually help the U.S. IT industry itself develop faster than it might normally, and so forth.
Grow our economy, grow our border protection, all those things.
All that stuff. So it's really been, that part of it is really fun.
It is. It explains why you're so involved and have your fingers in so many technologies.
It's our job to do that,
So can you tell us a little bit more at Los Alamos? I think it's fair to say you have 5, 6, 7 file systems, all for different kind of purposes. Maybe talk just a little bit about why would you have so many kinds of file systems in one environment? What kind of problems are you looking to solve?
The multiple types of file systems evolved because arguably we weren't smart enough to figure out how to do it with one. And the kinds of things we're talking about are things like home and project space. So, a lot of people mounting the thing and people compiling and having little data files and things like that, which is the classical NFS share space, right? It's not terribly hard to do. It was a solved problem a long time ago. And then, sort of at the other end of the spectrum, there's things like Lustre, and Lustre was invented for massive parallel checkpointing. And so it's really good at writing. Most file systems aren't really good at writing, but it's really good at writing, and it's really good at writing in an incredibly parallel way. And really, the hardest workload it has is the Los Alamos and one DoD site, where the entire 10,000 nodes, which probably today is 1 million cores, all write into the same file in different places. And it's kind of worse than that, because not only do they write into the file in different places, but they all write in sort of very close proximity to one another. And so they'll descend on one part of the file, and then they'll move down, and they'll all descend on the next part of the file. And so managing that coherently is what Lustre does. That's why it was invented. And that was a hard problem at the time. So hard that we didn't think we should go after anything else. Just build something for that. We'll use it for that. Of course, now it's used for more than that, but that's really what it's good at. But there's other storage systems, like a storage system to keep data around for years and years and keep it safe. Well, that's not what Lustre is for. It wasn't invented for that. You could make it do that, but that's not what it's for. You would use completely different erasure schemes and completely different, durability kinds of concerns associated with it. And so there's file systems or storage systems for long-term, data storage. And then there's file systems for distance. Peter Braum actually worked on Andrew file system AFS before he did Lustre, and AFS is sort of the original long-distance file system, right? And he even built solutions after that, Intermezzo. I don't know if anybody remembers Intermezzo, but it was the follow-on to AFS. And there are people that need that, right? And that is a whole different set of stuff. It's remote caching and remote cache management, and how do you deal with disconnected coherence and stuff. There's a whole different set of problems. So at any rate, there's a lot of different workloads, and 20 years ago we just attacked them one at a time and built solutions in that space. And to be honest, until 3 or 4 years ago, I never thought it was going to be possible to reduce the number of those types of storage systems. I figured there would always be ones for this and ones for that and so forth. And it's interesting that the NFS story has evolved to the point to where, just like in networks, the answer is Ethernet. Well, just like in storage, the answer may very well be NFS. Maybe for everything. It's super interesting. And
I think it's worth digging into that a little bit. So why is NFS so important, and maybe why now? You mentioned, it's 22 years now that it's been kind of coming along and being developed. Maybe talk a little bit about what is that kind of critical moment we've reached with the NFS technology and why NFS?
It kind of all goes back to the concept of separating data and control, which Lustre did, and it's been done many, many times. But the interesting thing about that way that's done, NFS, is it's coherent and recallable. And so a map is to show me where the file is, or show me where the file spread out over, or tell me where the locations of the file is. And that's useful, but it becomes incredibly powerful when it's coherent. In other words, if the storage server decides to change where it puts stuff, if you can just recall the map and tell people, hey, this stuff is moved, then you can move data around willy-nilly behind the scenes, and clients can be told about it, and they can know where to go get it now.
Right.
That's a very, very powerful concept, and from that gets all kinds of capabilities, like remote caching. You can say, let's put a copy out there temporarily. I'll put that in the map temporarily, and then we solve almost entirely the distance problem, right? But you can do the same thing for having 4 copies, right? And you could tell that there's even heuristics, and that's the one closest to you.
Right.
And so the map is the key, and the recallability of the map is kind of the important piece of the map. And the recallability was the hard part. So we had, NFS was stateless before all this began, and recalling things can't be done statelessly. It requires state. So that was a long road to get from statelessness to statefulness in an acceptable, performant way. These distributed systems are hard to do, and it took a long time to do. But now that that's there, it's opened up this huge, panacea of stuff you can do with it, which can address some of the workloads. And let me just give you an super interesting example. So one of the things we have that happens at our site is somebody will launch a job across 1 million cores, right? And it's going to happen.
That's an expensive job to launch.
It's an expensive job to launch. And it's interesting because that 1 million cores all start running a Python script. Now, they probably don't run a Python program when they get down to running the physics, but they all launch it from a Python script.
Right.
So there's a Python script that runs. And what the first thing that happens in a Python script is it goes and does 40 includes. If you're a Python programmer, you know what an include is. Well, what that does is that says, go pull in these other files, include these other files, right? So instead of 1 million, I have 40 million. But it doesn't stop there. Every one of those files it includes may have 40 more includes. And this may go on and on and on. And so you can easily end up with 1 billion file fetches just by launching this one, massive job. This is a read storm from hell, right? I mean, it's the definition of it. And so how do you fix these things? Well, you fix it through multiple copies and caching. Guess what? The map enables multiple copies and caching, fundamentally. And so NFS can go solve this problem because of the map, right? And it's a hard problem. If you didn't have this kind of caching and, making multiple copies and making cache copies and controlling all that, none of this would be possible. It would be hard to do. In fact, what people resorted to years ago was they wrote middleware themselves in their own applications to deal with this because there was no file system that would do it. Lustre won't do it, right? And so, anyway, it's interesting that one piece is so powerful.
And it's important, I think, especially with the contribution you make into industry, that the labs sometimes have people who can write like that middleware, but the general enterprise doesn't. They have not the skills, the time, the focus, or the experience. And trying to get some of this very specialized compute design and workflow design into a more standards-based solution is kind of helping to accomplish that mission of helping not just labs and very specialized supercomputers, but the AI industry, enterprise computing, things like that, right?
Yeah, I mean, you're exactly right. We have hero programmers at the lab because they're paid to be heroes. I mean, that's their job, to run, million core things, and they've been doing this for 30 years, so they're quite good at it.
Right.
But the world isn't headed that way. The world is headed towards, I downloaded this container that I didn't write, and I'm going to run that container and have it go do some magic stuff for me. And they don't even know what's in it.
Right.
Yeah. Or at most, that's the beauty. It works, right? And so if we can get to standardized solutions, then stuff like that is possible, and you don't have to have heroes anymore, because heroes are hard to keep. It's hard work. So yeah, absolutely. The world is not headed in the direction of heroes, and that's a good thing.
So you mentioned it was about 3 or 4 years ago that you thought what was probably going to be impossible. Maybe there was a light at the end of the tunnel, and collapsing the need for so many file systems and different technologies, there was the possibility we could do this. What happened 3 or 4 years ago? Was it the advancements in NFS? Was it some of the work that Hammerspace is doing? What was it that you were kind of caught your attention there?
It's an interesting story. So I spent part of my life in San Jose funding technology, and I was having a meeting with somebody, I don't even remember who, and they said, David Flynn wants to talk to you. And we set up a lunch meeting somewhere, and he said, Gary, we're using a bunch of your stuff. And we're finishing it, actually, and we're improving on it. Are you interested? And I at first I wasn't, because I thought, well, this is too good to be true 22 years ago, or whatever it was.
We've been at it for a couple decades.
Yeah.
What makes this the time?
And so you have to ask David why he looked at it and said, oh my God, there's potential there. I think that's what he's good at. But
it is.
He came and talked to me and said, this is super interesting, and we know you did all this work before, and we know that you probably know where all the thorns are, right? Mm-hmm. So could we, talk to one another about moving it forward? And so to be honest, I can't answer your question, because I don't know what caused him to see it, but he brought it to my attention that he had picked up the flag that I carried for 10 years or so, and is running with it, and incredibly fast. I mean, incredibly fast. And, the fact that he partnered with Tron is no surprise. I mean, we'd been working with Tron for, all that time. But
and now Tron is bringing other kernel maintainers on board. We have Mike Snitzer now, and, so there's some critical mass there.
And it's super good to, I think what's really cool about this is it's not just this HPC, DOE, government-type weirdos that are doing this, right? And AI is this big, huge thing, and everybody needs parallelism now, not just us. And the workloads are different, but the same tools can be used to solve those problems. And so it's kind of a refreshing to have a lot more people needing the same set of tools that we've been using for.
It is refreshing. New talent, new energy.
Yeah.
And I know part of the thing that David saw was, Linux won the operating system war largely. Linux is becoming the status quo and it's even running in like DGX nodes and things like that. So, as he saw the operating system war being won, then it was time to think, okay, well, what is it that we can do with the protocols to make these more standards-based? And there was kind of some of that, and David could speak much more deeply to it, but that was part of it, was just seeing that Linux is becoming standard everywhere. And if we can take proprietary solutions out and drive it into the operating system, there's a lot of efficiencies you can accomplish.
The reason we funded this technology initially was we wanted to try to get a parallel file system client into Linux, and not have a custom parallel file system client for Lustre, and not have one for GPFS, and not have one for Vanassus and whatever. And we didn't accomplish that. But that's really part of the power.
Right.
The fact that the client can be engaged in this activity makes this so much stronger than trying to make NFS just work in some sort of parallel way without having the client participate.
Yeah.
The client participation is just, that's why there's custom clients for Lustre and they're in the kernel and they're hard to get in, they're hard to maintain and stuff. Having one that ships on your Linux CD is truly, a godsend in a way, right? It wouldn't be this broad if that weren't the case.
And I think that's part of, there's enough impetus for it because there's so many more users of these big compute environments than just supercomputing and HPC now, that there's a lot of need to get it into industry standard operating system. Because if you think about a financial services institute, it's tough to get new things into their build environment, past their security teams. When it's a bank, it's different than a isolated research institute in some ways. And so I think that's part of the driver too, is you need the technology, but it needs to be something that's already vetted in kind of their build environment.
A lot of the world depends on POSIX.
Yeah, for
even
sure.
if they don't know it.
So
a lot of world does.
This is really like such a great opportunity, kind of hear behind the scenes what happens in one of the big labs leading the industry. Maybe as we tie up, we could talk a little bit about, Hammerspace calls it Tier 0, but we announced last week how to apply this technology to take advantage of the storage that's built into your compute nodes. Maybe you could just talk a little bit about why have you not really used local storage in your compute nodes in the past for your big HPC workloads?
We've avoided having storage in compute nodes on our clusters for decades. Initially, it was because of the file systems, the storage devices were very unreliable. They were spinning disks, right? And so that caused the mean time to failure for the compute nodes to be horrible. And so we wanted nothing in the compute node that moved.
Right.
Let's get the mean time to interrupt to be as low as possible, so that we don't have to do checkpoints all the time. We can just do them part of the time, and we can actually compute some, right? And so that's why we avoided it. Is the failure rate, but the consequence of failure is also important. And the consequence of you having data on a compute node and it fails, because it will, you lose access to the data. Right, and so we've avoided this like the plague forever because we couldn't deal with it. And the people that did do it did it themselves in their own middleware and their app. They would use pairs of neighbors to make copies with one another and all that kind of thing. But for the most part, HPC has avoided that like the plague.
Right.
And it has to do with failure at scale. And the whole reason that checkpoint and restart exist is failure at scale, right? And so, which is kind of humorous. It's interesting to hear the AI people complain about needing to checkpoint, which we've been doing for 30 years. But,
right. Some of the concepts are new to some where they're not to others.
But what would make using local storage possible is if you solved those problems, right? If you made it visible to other nodes, if you made it manageable from other nodes, and if you made it so that it's available whether the node's up or not, right? If you solve those problems, then it gives you the ability to use a local storage device in your compute node. And I think that's basically what you've done is you've solved those problems, and through NFS, which is also kind of cool. And so anyway, I think that, I mean, that's why we didn't use them, and that's why I think what you've done is different than anything that's been done.
Yeah,
in that
and
space.
you think about what Hammerspace has done with, it's a lot of contributions into Linux. Again, we keep coming back to that as kind of a common thread. And there's some neat benefits of if you can use your local storage and there's not much latency, your checkpoints go faster, and that's great. So you can actually compute, but you can't do that if the data that's writing isn't protected and available off the node either. And so we've really kind of thought about it as a two-pronged thing of make checkpoints fast, great, but that's the key thing was if you want to use that storage, it has to be immediately protected and globally visible, and that's what we've really integrated into our global file system. So it's kind of fun to talk about, wow, it's just another area that we kind of had written off as, well, we're not going to use it, but it's becoming a viable option, and particularly maybe interesting in environments where you're getting storage in your compute nodes, whether you like it or not, and you hate to have it just sit idle.
And that's becoming very common, right? You buy an HGX from somebody and they stick, some really large number of terabytes of flash in every node, whether you really want it or not. And it's useful if you can find a way to use it, but you're not going to allow, users aren't going to figure out how to use it in a very efficient way by themselves.
Right.
They're just not. If you can find a way to do it, but do it with, standard system software, so it's all taken care of for the user, then you can get value from it. And I think this is a super interesting thing because it's always been a niche thing that people solve for a particular application or something. It's never been a general purpose way to do, in node, storage. It's nifty.
Very cool. Hey, Gary, I know it's a busy week for you. I know you're not even a third of the way through your meetings, I think, for the week yet, or just right about at a third. Thank you for taking time to come on the podcast and share your thoughts. You've been out doing a lot of evangelizing this year. I know you're a frequent flyer to San Jose, and some of the conferences going on there, and the technology work that you guys are doing is really valuable. So thank you for coming on our show and sharing it with our audience.
Well, thanks for having me.
Thanks for listening to Data Unchained, powered by Hammerspace. To learn more, visit hammerspace.com. If you have a guest you would like to hear on the show, email me at molly@hammerspace.com.